Okay, so I'm just going to go through these and write the work on the paper. First one, for the reaction below, 2 moles of A, 3 moles of B are placed in a 6-liter container. At equilibrium, the concentration of A is 0.314 moles. These questions also are not in order of, I didn't separate out the conceptual ones from the numerical ones. I'll probably will do that though on your exam. So this one involves a calculation. We could set this up as an ICE table because it's giving us the initial values for the A and the B, and then the equilibrium value for the A. So if I do that, I can do that A plus 2B in equilibrium with C. So this is an ICE table where I can get the last line of this by doing a subtraction. Now, I could also use something like this if I wanted to calculate K, but this question doesn't ask for K. It just asks for the equilibrium value of B. So initially, A would be the 2 moles divided by the volume, because it's got to be moles per liter. So 2 over 6, that would be 1/3, which is 0.33. 333. And then B is 3 moles divided by 6, which is 0.5. And C we would say it starts out at 0 because it doesn't mention it in the problem yet. And then in the change, or the next piece of information we're given is this 0.314, which is actually the moles per liter at equilibrium. So that goes down here. This is 0.314. So obviously the A has decreased from 0.333 to 0.314. And that means B will have decreased as well, and C will have increased by that much. Now, we don't really need to know C for this question, but now A would have decreased by whatever the difference is between those. So I got to do a calculation to get the difference. So if I subtract those two, then I get 0.019 for the change in A. So that's a minus X. Now, and this is X, okay? So this 0.314, that is our X value. Now B has a 2 in front of it, so you have to remember that change would be minus 2X. So the equilibrium value would be 0.5 minus 2X. Okay? And we got to see what that is then. So we have to multiply 0.314 by 2. I'm sorry, we have to multiply the 0.019 by 2. So this is going to be 0.5 minus 2 times 0.019 for the B. Okay, so concentration to B at equilibrium is going to be 0.5 minus 0.038. So that's 2 times the change. And that's 0.462. Okay, and so that's closest one is this one. There's some rounding differences. Number 2, which expression correctly describes the equilibrium constant for the following reaction? Okay, so this is a reversible. These are all gases, so they all go into the expression, even the water. So you have products over reactants. You have a 4 for the NO and a 6 for the water. So you're going to look for those as exponents. Let's see, that would be the NO and the water have to be on top. They're on top. There's the 4 and the 6. And then the ammonia has a 4 and the oxygen has a 5. So that would match this as well. And so it looks like this is the answer for that one. Okay, number 3. For the reaction at equilibrium is found the concentration of bromine, chlorine, and BrCl are the following. So here, they're giving you all of the equilibrium values. You don't have to set up an ICE table for this. You just have to write down that the K K sub C value for this would be equal to the product squared, BRCL, or divided by the reactants, bromine, and the chlorine. And those are both to the first power. So that's going to be the 2.05 times 10 to the minus 3 squared divided by times 10 to the minus 5, which is A. Okay, so number 3, the answer to number 3 is A. 4, if K sub C equals 0.145, for this reaction, A2 plus 2B goes to 2AB. What's K sub C for this reaction? 4AB goes to 2A2 plus 4B. So you have to recognize that there's a relationship between the two reactions. Okay, they both have the same things in them, but this second reaction is the result of turning the first one around, which is kind of like multiplying by -1, and then also doubling all the coefficients. So with both of those changes, your new value of K sub C, I'll call it K sub C prime, would be the original K sub C to the -2, because you turned it around and it was also doubled, and those go as exponents here. So that's going to be equal to 1 over the original 1 squared, which equals 1 over 0.145 quantity squared, which is 47.6. Okay, number 5, what is the Kp expression for the following equilibrium? So here you gotta be careful to notice that the titanium is a solid. Chlorine is the only gas in here because the product's a liquid. So they're asking for K sub P. The only thing that affects the equilibrium expression here is the gas. So it's products over reactants. Now in this time, the product, because it's a liquid, you just put a 1 there. And the reactant, you'd write it for K sub P, the partial pressure squared of the chlorine, and this one would not enter in. So it should just be 1 over pressure of chlorine squared, which would be this first one there. Okay. Right, number 6. For which of the following values of the equilibrium constant does the reaction mixture contain essentially products? The concept here is the bigger the K value, the more products there are. So you just look for the one with the largest K value, which would be this one. 7, you have this reaction. You're given the mass of all these things in here. They're all the same mass, and they're all in a 40-liter container. So for this one, they're asking what's going to happen, because these are all initial concentrations, initial amounts. They give you the K sub P here. So the idea here is that you want to calculate Q from the initial amounts and compare it to K. So your Q value is going to be the partial pressure of the product, so the CH4, times the partial pressure of the C6H14 over partial pressure of C2H6 and the C5H12. Now, unfortunately, we got to do some calculations here to get the moles on each of these. Let me do that real quick. So I'm just going to do moles first, and then we'll convert them to molarities. So for the first one, okay, so those are all moles. That would be the N that would go into the PV equals nRT. So to get the pressure of each of these, I do our nRT over V. So for this one, it's going to be 1.94 times 0.0821 times the 500 divided by the 40. Okay, so those are the four pressures that would go up into there. When I put those numbers up in there, okay, so the last two be divided by the first two up here, 0.27. And now we compare that with K. We see the Q is less than K. Okay, so 1.27 is less than 9.57. It's a less than sign. And so that means the reaction is going to go forward. Anytime Q is less than K, the reaction goes forward. And so that's what we would look at here. Q less than K, more product will be formed. That would be the correct answer. There's also an answer here. Q greater than K, more reactants will be formed. That would be true if Q was greater than K. But it's not. For 8, hydrogen iodide undergoes decomposition according to that equation. The K sub P for this is 0.06. Suppose 0.317 moles of HI is placed in a 1.5 liter container. What is the equilibrium partial pressure of IUD? Okay. So we have a K sub P, and we have initial values, and we're asked what the equilibrium values are. So this is an ice problem in terms of a K sub P value. So I'm going to do the ice table down here, but I'll have to calculate the pressures that go into the ice table. So we got 0.317 for HI. So we just need to convert that into pressure. So we can calculate the initial pressure of the HI from that number. We're using the ideal gas law. So P would be nRT over V, which would be the 0.317 moles. And the volume is 1.5 liters. So that gives a partial pressure of 10.4 atmosphere. The HI. So that's our initial value of HI. And then we start these at 0. And then it goes to the right. So now this has a 2 in front of it. So this would be minus 2x. So these would be plus x. Minus 2x and x. So that's going to set up our second order equation that we need to solve this ice problem. So we have x squared over 10.4 minus 2x. Quantity squared equals our 0.06. Now this is one of those that fortunately turns out to be a perfect square on both sides. So we could take the square root of both sides as our simplifying step on this one. So that means this would become just x over 10.4 minus 2x equals plus or minus the square root of that, which is 0.25. Okay, so we can get two solutions there. So our x, if we use the plus, would be 10.4 minus 2x times 0.245. 0.55 Okay, and then if I bring the 0.49 to the left, I get 1.49x 5. So for the plus sign, the x would be equal to 2.55 divided by 1.4, which is 1.71. Okay, now that's probably the answer because that would give you positive answers for everything. Without going through all the details for the steps, so the negative would give us a negative x, which it can't be because we'd have a negative concentration. So 1.71 would be our value of, would be the answer because that would be the equilibrium partial pressure. And that's answer B. So number 9, carbon monoxide is toxic because it can successfully compete, blah, blah, blah. So this is a concept question. This shows a reaction between hemoglobin and carbon monoxide and the products that you get from that. So one of them is oxygen. So this is a Le Chatelier's question. It says, how is carbon monoxide poisoning reversed? And basically what it's asking is what would shift this to the left? So that would either be taking away some of the reactants or adding some of the products or changing the pressure. But if you look at the number of moles, you have 4 gases on the left and 4 gases on the right. So changing the pressure would actually not shift it either way. And we don't know whether it's exothermic or endothermic, so we can't do anything with the temperature. So it's just a matter then of adding or subtracting things. So now we could increase the oxygen pressure. And if we did that, then that would shift it to the left because oxygen is a product. So that would be reversing it. If we decrease the amount of hemoglobin, well, hemoglobin itself isn't in here as a reactant or product, so that's not going to change it. Carbon dioxide pressure, if we increase that, carbon dioxide is not in here either. Carbon monoxide pressure, that carbon monoxide is in here, but that would shift it to the right, which we don't want to do, or increasing the amount of hemoglobin. So the only one that is in this reaction and would shift it to the left would be the oxygen, increasing the oxygen. Number 10, which of the following would not be affected by volume changes at constant pressure? So for this one, we're looking at the delta N equals 0. That's what we're trying to figure out for which of these does delta N equal 0. On the first one, you have 2 moles of gas on the left and 2 moles of gas on the right. So that is a delta N equals 0. That would not be affected by volume change. So that should be the answer. Let's look at the rest of them just in case. Here you have a 1.5 on the left and a 1 on the right. So that has a delta N. Here you have a 1 because oxygen is the gas. And that's all, just oxygen on the left. So that would be affected by volume change. Here you have 2 plus 1, you have 3 on the left and no gases on the right. So that wouldn't be the answer. And here you only have a gas on the right. So that also would be affected. So it's just A that has the delta N of equal to 0. That one. Number 11, which of the following would be affected by volume changes at constant temperature? So it's really the same kind of question, but just phrased a little differently because you have 3 choices here. So again, you're looking at delta N equals 0. Is not equal to 0, actually, because it's saying would be affected by volume change. This one said it would not be, so we were looking for it delta N to be 0. Here we don't want it to be 0, to be a choice. So here you have 2 plus 3, you have a 5 on the left and a 2 on the right, so that would be affected. That's one of them. Here you have 1 and 1, a 2 on the left and a 1 on the right, so that would be affected by volume change. So again, both of these are delta N not equal to 0. This one has 1 plus 1 has a 2 on the left and a 2 on the right. So this last one is delta N equals 0. Okay, but we're looking for the delta N not to be 0. So that's 1 and 2. Another Chatelier's principle question. Here you have a reversible reaction. It's all gases. You have a delta H value and then a case of P. Which of the following would be true if the temperature were increased to 100 degrees? Now this actually it's kind of Le Chatelier's, but also it's understanding how the equilibrium constant changes with temperature. So if you have a reaction in which the delta H is positive, that means it's endothermic, which means you could write the word heat over on the left. That's endothermic. For an endothermic reaction, if you're increasing temperature, okay, so you're starting at 25 and going up to 100, that's increasing temperature. Your temperature is going up, kind of putting pressure on the left, that's going to shift the reaction to the right. A shift to the right means your K value is getting larger. So your K has to increase with that temperature change for it to go more to the right. So the value of K would increase. That would be your one answer. Concentration of ICL would increase. That's not true because that's going to go down. Partial pressure of iodine would increase. That actually is also true because it's going to shift to the right. Okay, so 2 of these statements are true, 1 and 3. Number 13, one method for the decomposition of carbon dioxide is that, this is another Le Chatelier's. You have a gas, a gas, a gas. They give you the delta H, so again, you know it's endothermic. And we could write heat on the left-hand side here, because that's a positive value. Which change will cause an increase of carbon monoxide? So that means you're looking for a shift to the right here to get carbon monoxide. Adding more oxygen, no, that would do the opposite. That would shift it left. Adding a catalyst. Catalysts do not shift the reaction forward or backwards. They would just change the rate. Removing carbon dioxide. Carbon dioxide is a reactant, so if you remove that, that would shift it to the left also. Increasing the pressure. So let's see. Now here we have to look for the delta N. So our delta N here is 3 minus 2, which is positive, so it's positive 1. So if we increase pressure, it would shift the system, and what it would do is it would shift it in the direction away from the higher number of gases. So it would shift it to, it would also shift it to the left, which isn't what we're looking for. And the last one, increasing the temperature. Increasing the temperature, that's the one that would put pressure on the reactant side and would shift it to the right. That's what we're looking for. No. So that's a good question. It has a lot of different aspects to it. Number 14, what is the conjugate acid of HPO4 minus? Easy question. Conjugate acids, you just have to add an H plus to whatever you're given, and then you get the conjugate acid, which would, for this one, be E, H3PO4. Which acid has the strongest conjugate base? Now this one is this question comes from that section in the book talking about the relative strengths of acids according to the structure of the acid. Here you have several acids. Now, one of the first thing you can do here is identify any of these that you know are what would be considered strong acids. And you should know what the strong acids are. You should know the common strong acids. Those are the binary acids of chlorine, bromine, and iodine. So that'd be HCl, HBr, and HI. And then also sulfuric acid is a strong acid. So is nitric acid and chloric acid is also a strong acid, which isn't here. But you do have some strong acids here. So you have nitric acid is a strong acid, HI is a strong acid, H2SO4 is a strong acid. Now, this is asking for what the strongest base is. If you have a strong acid, what I just went through in the recording I made is that strong acids have conjugate bases that are neutral. So if you're looking for the strongest conjugate base, it's not going to come from any of these three. So you can cross those out because those are all strong acids. Their conjugate bases would not be very strong. So that just leaves this one and this one to compare according to their structure. And so you have HOCl, which has the structure of it is like this, and then you also have HOI. Okay. Remember, I said that the size of the atom is important if you're looking at comparing what's directly connected to the hydrogen. On this one, though, both of them have oxygen that's connected to the hydrogen, so there's no difference in the size of the atom there. The other thing you look at is electronegativity. And so the chlorine and the iodine, those do have different electronegativities. The chlorine is more electronegative than the iodine, which means it's pulling electron density towards itself, which makes the bond weaker to the hydrogen. Meaning that this one, because the chlorine is more electronegative, this is going to be your stronger acid. Now, that's not the answer to the question, though, because the question says, which is the strongest conjugate base? Since this is the stronger acid, that means the conjugate base of this would be stronger. Because the stronger the acid, the weaker the conjugate base. So the answer is actually the conjugate base of this, which is OI minus. Okay, this is a weaker acid, which means this is going to be a stronger conjugate base than the OCl minus would be. So that's your answer, is the HOI is the answer because it has the stronger conjugate base. It's the weakest of all those acids, in other words. So it has the strongest conjugate base. That's a pretty complicated question. Lot to understand in here to get it right. Number 16, which of the following statements is incorrect? So this also has to do with the structure of acids and their strength. It says HCl is a stronger acid than HF, which is true. And it's because HCl bond is weaker than HF, which is true. Okay, so that's a true statement. The weaker the bond, the stronger the acid. This is asking for what's incorrect. Fluoride is a stronger base than chloride. Okay, that's also true because HCl is a stronger acid than HF. One reason why HCl is a stronger acid than HF is that chloride is more electronegative than F. Okay, it's true that HCl is a stronger acid than HF. So that can't be the reason because that second part of the statement is not true. Two acids, HBr and HI, both appear equally strong in water. This actually is true, even though they're not the same. One acid is stronger than the other. When you have any strong acid in water, any strong acid will completely ionize. So this is actually a true statement. C is the one that's not a true statement. Let's look at E. One reason why HCl is stronger acid than HF is that chloride is a larger atomic radius than F. That is true, because chlorine is larger, and it's the size of the chlorine that makes it a stronger acid. So this is the one that's not a true statement. Okay, number 17. These are pretty straightforward and easy. These first few anyway. What's the hydronium ion concentration if you have barium hydroxide? So the first thing you can do is determine the hydroxide ion concentration, because that's going to be 2 times this number. Because the barium hydroxide breaks into 2 pieces. Okay, now that's not the answer because they're asking for hydronium ion. Okay, so this gives us 0.0076 molar of hydroxide ion. Okay, but hydronium ion is H3O plus or H plus. So we do know the relationship, though, that the concentration of hydronium times hydroxide is equal to Kw, and we can calculate hydronium ion concentration from that. So the concentration of H3O plus is the Kw divided by the hydroxide concentration that we just calculated. See? Okay. So we used this relationship here to do that. And, you guys are going to have that same formula sheet that's posted on my courses. You take this test. Number 18, the hydronium ion concentration is this. That's the H plus, in other words. What's the pH? So this is H plus or H3O plus. So you just apply the definition of pH minus the log of that number, 5.6. Which of the following salts will produce a neutral solution when added to pure water? So here you have to look at compounds that would have the cation being just a simple group 1 or group 2, because that means it would be neutral. And then the anion being the conjugate base of a strong acid. Okay, so let's look at these. Here lithium would be neutral, but the HCl3, that's not the conjugate base of a strong acid. Okay, the conjugate base of that is carbonic acid, which is a weak acid. Here you have NH4, which isn't neutral. That's acidic, so that's not the answer. The sodium here would be neutral, but the sulfate is not. The sulfate comes from a weak acid, HSO4 minus, so that would be a basic. Rubidium part on this one would be neutral. The nitrite, NO2, isn't neutral, because that comes from HNO2, which is a weak acid. Here you have potassium, which is neutral, and nitrate, that is neutral because it comes from nitric acid, which is a strong acid. So that's the answer. This one, because it has an anion that comes from a strong acid, and then it has just a simple 1 cation. Number 20. Solution has a pH of 10.8. What is the hydroxide ion concentration? So you're looking for a hydroxide ion, that's OH minus. Okay. pH is the negative log of hydronium ion. So there's a couple ways to do that. You can do it sort of like up here, except reverse, where we would be solving for OH minus instead of H3O plus. To do that, you'd have to calculate the H plus concentration using 10 to the minus 10.8. A little more direct way of doing this, though, is to determine pOH from the pH. pOH would be 14 minus the pH. Okay, so you're using a formula that pH plus pOH equals 14. So then you subtract to get the pH. 14 minus 10.8 would be your pOH, which is 3.2. Okay, so that's pOH, which means hydroxide ion concentration would be 10 to the minus pOH, which is 10 to the minus 3.2. Make sure you can do these things on your calculator. Know where the keys are. So this is giving me 0.0000631, which is this one, 6.31 times 10 to the minus 4. Number 21, 0.1 molar aqueous solution has an HA has a pH of 4. What is the value of Ka? All right, so I did these kind of calculations in class. I'll just write out the equilibrium here to remind you of why we can do it this way. Okay, this is sort of like calculating K sub C in the chapter 16. Kind of think about it as an ice table, where the initial value of HA here is 0.1, and you have 0 and 0. This would be minus x and plus x. This would be 0.1 minus x, x, and x. Now here you're given the pH of 4, and that's how you can calculate x. Because this means your hydrogen ion concentration at equilibrium is equal to 10 to the minus 4, which is 1 times 10 to the minus 4. Okay, that is our value of x. 10 to the minus 4, 1 times 10 to the minus 4. So that goes in here. So our K value is equal to x squared over 0.1 minus x. That value is so much smaller than 0.1 that this just stays as 0.1. The top part there is 1 times 10 to the minus 4 quantity squared over 0.1. Get rid of that x here. I can write the answer, which is 1 times 10 to the minus 7. E. Okay, so we did something like that in class. So it's basically you use the pH to get your hydronium concentration, which is your top number, and that's squared because both of these are x, and then your bottom number is just your concentration of your solution. Okay, hypobromous acid has an acid concentration constant, 2.5 times 10 to the minus 9. What is the hydronium ion concentration? So this is an ice problem, which will be R for a weak acid. H plus and OBR minus. Okay, CE. The initial here is the concentration 0.63 molar for HOBR. We start at 0. This is minus x and plus x. And x. So your overall expression here would be x squared over 0.63 minus x equals this number, 2.5 times 10 to the minus 9, which is a very, very small number. So you can either solve this exactly with the quadratic formula, or we could make the assumption that x is small. And in that case, it becomes easier to solve. It would be x squared over 0.63 equals 2.5. 10 to the minus 9. Okay, so what we're doing there is that we're going to assume that x is much smaller than 0.63. Oops. And then we solve for that. So x squared equals 2.5 times 10 to the minus 9. 63.58 times 10 to the minus 9. And then we take the square root of that to get the answer. So x equals, which is let's see, which is 3. Okay, so that's your X value. Now this asks for the, yeah, that asks for the hydronium ion concentration. So that would be your answer. They probably have it as 4. Yeah, 4 times 10 to the minus 5, which is A. What is the hydronium ion concentration equilibrium in a 0.72 molar solution of aniline? So aniline is a base. And you know, how do you know that? Well, you know that because you're not given a Ka here, you're given a K sub B. It's a little B there. So that tells you to write this equilibrium out like this. C6H5NH2 plus water to C6H5NH3 plus. So you pick up a hydrogen on this one, leaving behind the hydroxide. Right? And then this is another ice table. Initial concentration is 0.72. Start with 0 and 0. Minus X plus X. 0.72 minus X, X, X. Okay, so again, we set it up. X squared over 72 minus X. This time it equals the KB, which is this number. 2 times 10 to the minus 10. That's also a very small number, so we can assume X is much smaller than 0.72. So 2 times 10 to the minus 10. Solve for X, so you multiply here. So X squared is 0.72 times that. That's E 0 times 10 to the minus 10. And then that means that X is going to be the square root of that. 0.79, or sorry, 1.74. Times 10 to the minus 5. Okay, now what's the question here is asking for hydronium ion. This is hydroxide ion concentration. We're looking for H plus here. Okay, so we have to calculate H plus from that. So this is where we're going to use that relationship we used previously. This would be 1 times 10 to the minus 14 over this value on the bottom. So over the hydroxide concentration. That comes out to be 5.75 or 5.8 times 10 to the minus 10, which is C. Okay, now notice that the 1.7 number is in here as a possible answer, but that's not the right answer. Don't be too quick to pick an intermediate number that you got. Make sure you pay attention to what the question's asking for. And for that one, it was asking for hydronium. All right, one more here. This is another ice problem. This one, though, is where you're going to solve for pH, but it's in a solution that has a conjugate base in it. So it's going to have a base that has a charge on it. That's potassium nitrate. Potassium nitrite is KNO2. And the potassium part doesn't matter, but the NO2 does. Because this is going to give you the NO2 minus, going to give you the anion, which is a conjugate base. So your equilibrium here is going to be NO2 minus plus water. And that's going to act as a base. It's going to pick up the H and leave behind the hydroxide, making the solution basic. So we're going to do an ice problem here to figure out what the pH is. Now, there's a couple curveballs here that you got to be careful about. First of all, they're giving you the mass of the potassium nitrate and the volume. So you got to calculate the molarity here to put in your ice table. And you have to use the mass of the whole thing, because that's what the mass, the grams, is for. So potassium nitrate, you have to go to the periodic table and add up those values for the molar masses. That's 85.1 gram per mole. So that means the moles here would be, it's the number of moles would be equal to 1.67 grams. That's 1 mole over 85.1 grams. Number of moles is 0.0196 moles. Now that's in 185 mils of water. So to get the molarity of this, molarity of the nitrite, that's going to be the same number of moles, because that comes from the potassium nitrite, 0.0196 divided by this volume in liters, which is 0.185. So that's 0.106 moles per liter, and that's what goes in your ice table. The water doesn't matter. These start at 0. This would be minus x and plus x. So our expression would be x squared over 0.16 minus x equals. And what this has to equal is the K sub B. If you look back in the original problem up here, they don't give you K sub B. They give you the Ka of nitrous acid. So you have to do another little side calculation here to get Kb. And you use the relationship to Ka times Kb equals Kw. So you got to calculate Kb first. It's going to be 1 times 10 to the minus 14 over this number up here. 10. That's 2.2. It's 10 to the minus 11. That's your Kb. So that this equation is x squared over 0.106. Now I'm going to go ahead and make the assumption that x is small, because your Kb number here, that is a very small number. So when I bring this down, I'm just going to get rid of the minus x part. Equals 2.2 times 10 to the minus 11. Now I solve for that. So x squared equals 0.106 times this. This is an 11. It looks like a 4, but it's not. .3 times 10. Okay, so x would then be the square root of that. 0.5 times 10 to the minus 6. Okay, now they're asking for pH. This number we just calculated is molarity of hydroxide ion. Because remember, this is a basic solution. So your X here is hydroxide. You got to do a little bit of work to get this turned into a pH. So there's a lot of different steps here. What I'm going to do first is take this and I'm going to use it to calculate a pOH. So that would be minus the log of this. So the pOH would be 5.82. Now, if you look up here in your solutions and you go too fast, you might choose 5.82, but that's not the right answer because that's the pOH. To get the pH, we subtract that from 14. We go down here, we subtract this from 14. So I'm gonna just do that up here. So my pH equals 14 minus 5.82, which is 8.18. So that's actually the answer. A lot of different steps. And that's this one. Makes the answer. Number 24 is E. And that, ladies and gentlemen, concludes the practice test. I can't even fit it all. Just to get it all in one shot here. The whole thing. See you on Thursday.